In this module, I want to talk to you guys about ionic bonding and how this relates to lattice energy, what lattice energy is, and how Coulomb's law affects all of these things. Okay, so Coulomb's law is really the driving force behind a lot of the stuff we've been talking about with things like effective nuclear charge, atomic and ionic sizes, ionization energy, electron affinity, um, electronegativity, all of it. Okay, Coulomb's law is kind of behind the scenes of all of this. But I'll define what Coulomb's law is in just a minute. But first, I want to talk a little bit about what lattice energy is and how we can see this play out as well. So we're going to be dealing with ionic compounds, which means cation anion combination. Again, ionic means cation plus anion. But we're specifically going to look at binary ionic compounds. So a binary ionic bond. Binary just means between two species. Binary means two. And because I'm dealing with just two things, and I have to have a cation and an anion here, this really means between a metal ion and a non-metal ion. So I'm going to deal with the ionic bond between these two atoms, okay? So I've got a metal atom that has now made a metal ion, and a non-metal atom, which has made a non-metal ion, which again, metal ion is also known as a cation, non-metal ion also known as an anion. So it's not really that they're atoms anymore. They are the ions. We are looking at ionic bonding here, but the word binary itself just means two atoms. So that's where this is why we keep using the word atom in here. I need you to understand that in this situation, I'm talking about ions, not atoms. There are three things you need to consider in terms of energy when you're looking at lattice energy. And again, I will define what lattice energy is in just a sec. But metals have low ionization energies. That means that they willingly give up electrons, at least compared to their non-metal counterparts. Non-metals have high electron affinities, meaning they willingly accept electrons, at least compared to their metal counterparts. And energy is released when gaseous ions form the solid crystal. So what I mean by this, like if I take Na plus in the gaseous phase, I combine this with a chloride ion in the gas phase, it will form NaCl. And it does this plus heat or energy in the form of heat. Okay. What is lattice energy though? I keep saying I'll define it, so let's define it. Lattice energy is defined as the energy required to completely separate 1 mole of a solid ionic crystal into the ions far removed from each other. So I have 1 mole of sodium chloride. Remember what sodium chloride really looks like. We've got your little, your sodiums is, sorry, I'm trying to make little circles here. And opposite that, you've got your slightly bigger chlorides, and they're alternating in this crystal structure. So you've got that alternating 3D array for the ionic compound. I want to take an entire mole of these and I want to break this up so that I remove all of the sodium ions from all of the chloride ions, specifically in the gaseous phase. Why in the gas phase? Because in the gas phase, they have the highest amount of energy. It's easiest to remove these things away from each other and act so that they're no longer attracted to each other. We'll talk about IMFs or intermolecular force in a future chapter, but that's what keeps these compounds together in the solid and liquid phases. We need them in the gas phase so we can really truly separate them out from one another. So we need to, what is the energy required to separate these out? How much energy does it take to break apart this crystal and break these ions away from each other? And that is a measure of your ionic bond. So how does lattice energy relate to some of the physical properties of ionic substances? Well, the higher that lattice energy, meaning the more energy to break these ions away from each other, generally speaking, the higher melting point you're going to have, because it's going to take more energy to melt the compound because more energy has to go in to break the ions away from each other. It will also be a physically harder compound. What I mean by harder is like when you push on it with, if you take, say you got the surface of the material and you've got some kind of thing pushing into it, we can actually measure the hardness of the material. It's physically harder material because the compounds want to, the ions in that compound want to stay together. The ions don't want to be separated. Do not forget, this is important to know all throughout Chem, no matter Chem 1, 2, organic, I don't care where you're at, you need to remember this. Bond breaking is always endothermic. That means that to break bonds requires energy. Bond formation is always exothermic, which means that when bonds form, energy is always released. So you can think of lattice energy in this way. It's a measure of the strength of the ionic bond. How strong is that bond? The stronger the bond, the more likely those ions want to stay together. The more energy I have to put in to break them apart. Okay, why do I keep talking about Coulomb's law? This all relates back to Coulomb's law. There's a great PhET simulation, and I highly recommend you check this out, play with it, see what it looks like, and you can really explain Coulomb's law very well for you guys. But Coulomb's law states that the electrostatic force of attraction between charged particles is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. What does all that mean? It means this equation down here. Okay, that's what that means. Basically, it means that charges on the ionic species is important. The larger the charge I have, the more attracted they are to each other. The distance between these species is also important. The larger the ionic radius of a species, the further it is from something, the less charge attraction it will have. Remember, force times distance is equal to energy. So your potential energy between the charged particles is directly proportional to the product of the charges, inversely proportional to the distance between the charges, where Q is each charge and R is the radius of each atom. The big idea behind this, the closer an electron is to the nucleus, the stronger the attraction and the lower the electron's energy. That shouldn't surprise us. But remember, what we're talking about here is we're talking about the protons and neutrons in one species. They're in my nucleus, right? And then I've got my energy levels where my electrons are residing outside of that. This is attracted to another species which has its own set of protons, neutrons, and its nucleus and electrons here. So it's the electrons from this guy. Let's say this one has an extra electron, this one is a hole. It's the electron from this species that's attracted to the nucleus of this species. The bigger this is, the further they are away from each other, the less that pull will be because they're further away. So the larger the radius, the less the pull on the atoms. The lower the lattice energy, the easier it is to break apart. The greater the charge difference, have a greater lattice energy, the harder it is to pull it apart. So again, force is equal to K, which is just a constant, proportionality constant, times Q1 over Q2. Q1 is the magnitude of the first ion you're looking at. Q2 is the magnitude of the second. What I mean by magnitude is it +1, +2, +3, whatever it may be. R is the distance between the two ions. So the distance between looking at your nucleus of one to the nucleus of the other, what is the distance between those ions? The interaction between the atom's positively charged nucleus and an atom's outermost electrons is what makes each atom behave in unique and often predictable ways. So the repulsion between the electrons is what makes it predicting the behavior more difficult. If we were just looking at an electron here being attracted to, protons here, no problem. But we can't forget that this also has electrons here. This also has an electron out here that's kind of saying, yeah, you know what? I'm going to block you from seeing that. I don't want you to come over here. So it's this attraction repulsion force that we're dealing with. It's this electron is absolutely attracted to this proton in the nucleus. See if I can find a color. But I do have this electron and others that are repelling it as well. So it's this balance between the attractive forces and then the radius or the distance between the atoms. That's going to lead to your lattice energy. So let's talk through it. To predict lattice energies, you are actually applying Coulomb's law. Generally speaking, the greater the ionic charge, the higher the lattice energy. Generally speaking, the larger the ion, the lower the lattice energy. And what I mean by larger is greater ionic radius. Here, I mean +1 is less than +2 is less than +3 or 4, 5, whatever you may go up to, okay? Remember, charge is usually more important than size. So if you've got comparable sizes, go with charge. Charge is going to be the most important thing here. So let's look at these values. If I look at sodium chloride, the lattice energy of sodium chloride is 786 kilojoules per mole. That means to separate out 1 mole of sodium ions from 1 mole of chloride ions in the compound of sodium chloride, it would take 786 kilojoules for every 1 mole of material. If I look at Ki, let me look up Ki really quick because I do not have that one written down. So lattice energy, Ki. I know it'll be smaller, I just don't know its actual value. The Ki value for Ki, it's 649 kilojoules per mole. So all I've done here, if I look at the periodic table, and again, you should always have the periodic table when you're studying, but when you look at the periodic table, you've got sodium above potassium, which means potassium is larger. And then if you look at your halogens, chlorine comes before bromine, comes before iodine. So iodine is definitely larger as well. And what I see is what we've said, that generally speaking, the larger the ion, the lower the lattice energy. Overall, for Ki, I get a lower lattice energy than I do for sodium chloride. Now, what if I looked at something like magnesium chloride? Magnesium chloride has a lattice energy of 2,526 kilojoules per mole. That's a huge jump. Magnesium is one spot over on the table. So I've continued my table here. Now I'm in magnesium, which is smaller compared to sodium. And the chloride is common ion here. But here I had a +1, -1 difference. Here I have +2, -1. So here it is a charge effect. I see a much bigger difference because of that charge there. And then CaI2, let me look up that one because I accidentally deleted all of my notes for this chapter behind the scenes, and I want to make sure I'm writing down the right actual values for you guys. Okay, calcium iodide has a value of 2,087 kilojoules per mole. So again, calcium is bigger than magnesium. So if I'm going down the table, calcium's down here. Iodine is bigger than chlorine. We found that out before, right? It goes chlorine, then bromine, then iodine. So iodine is larger. They're both larger. So I see that size effect here, but I also see the effect of charge here. So again, +2 to -1, +1, -1. So charge is more important than size. And then this, so greater charge, greater charge difference, greater at lattice energy. And then from there, smaller size, larger lattice energy. And remember, this is due to Coulomb's law. They're both due to Coulomb's law, but this one is more pronounced for Coulomb's law. I think I spelled his law wrong, but that's okay. For Coulomb's law, it's you've got the electrons of one ion that are charged with the nucleus of a different species. So the smaller they are, the closer those ions can actually be to one another, the greater pull they'll have, and therefore the greater lattice energy. Let's take a few examples. Arrange the following ionic compounds in order of increasing lattice energy. First thing I do is I look at charge. I've got NAF +1, -1. I'm going to write them up here just because otherwise they're going to get convoluted down there. +1, -1. I've got CSI +1, -1. And I've got CaO +2, -2. So I want them in order of increasing lattice energy. I know calcium oxide is going to be the greatest. Why? Charge. It's the only one that's got a +2, -2 charge going. Now I'm into systems that have the exact same charge difference. So now I have to look at size. I know the smallest difference in size will have a larger lattice energy, which means the larger ions will have the smallest lattice energy. So cesium iodide will be small, will have a lower lattice energy than sodium fluoride because it's a larger compound. So again, sodium fluoride has that larger lattice energy, and then calcium oxide the highest. Let's see, number 2, which compound has the greatest lattice energy? Silver chloride copper 2 oxide, or chromium nitrate, chromium 3 nitride. Let's see, silver chloride is a +1 -1 combination. Copper 2 oxide is a +2 -2. And chromium nitride, nitrogen is a -3, so chromium is a +3. So the greatest here would be that chromium 3 nitride. And our last example, based upon a consideration of lattice energy, which compound is expected to have the higher melting point, NaCl or NaBr? And when I look at charge here, they're both +1 -1. So there's no difference in charge here. It doesn't matter on charge. I'm going to have to look at size. They both have sodium. So the only difference here is really that chlorine, or chloride in this case, versus the bromide. Bromium is lower on the table, which means bromide will still stay larger than chloride. So this is the larger size. This is the smaller size. So NaCl, sorry, it's hard to write at the bottom of the screen. NaCl will have the larger lattice energy, which leads to the higher melting point because it's going to take more energy to melt the compound, to break those apart, to break apart those ions. Okay, let's talk a little bit about covalent bonding. So that's ionic bonding, how it works. Covalent bond is formed when atoms are shared, though, when atoms are sharing an electron. So one bond shares two electrons. Covalent bonds typically seen between two nonmetal elements, but we will see examples where it's actually happening between metals, elements that we've considered to be metals, because again, bonding is a spectrum, okay? There are two measures of the strength of a bond, though. We look at bond length and bond energy, which is also known as the bond dissociation energy. The shorter the bond, the stronger the bond. So let's look at a carbon-carbon single bond versus carbon-carbon double bond versus carbon-carbon triple bond. Most species can singly bond. Noble gases don't really would like you to leave them alone. There are a few there is like xenon will bond with things, but otherwise noble gases like to be left alone. Most things will single bond. Some things will double bond, and a few things will triple bond. Carbon will do all three. A carbon-carbon single bond has a bond length of 154 picometers. Remember, pico is times 10 to the -12. We usually report these in angstrom, but we don't require you guys to learn angstrom here. So 1.54 angstrom is how you're usually going to see it. 1 angstrom is 10 to the -10 meters. 1 picometer, 10 to the -12 meters. So I don't care how you want to report it. I'm just going to give you in picometers because that's what you guys have learned this semester is picometer. 154 picometers, and the bond energy here is 348 kilojoules per mole. What that means is it takes 348 kilojoules to break apart 1 mole of carbon-carbon single bonds. If I look at a carbon-carbon double bond, its bond length is 134 picometers. So I see that shorter bond length. I should see a higher bond energy, and I do. It's 614 kilojoules per mole. Notice it's not directly double, and it's because a single bond and a double bond are actually different types of bonds, and we will talk about that soon. But we have things called sigma bonds and pi bonds, and sigma bonds are the strongest. Your single bond is your sigma bond. When you have a double bond or triple bond, you have pi bonds present, and they're just a weaker type of bond. So it's not a direct doubling of the energy, but it is a large increase in energy. Then our last one, a carbon-carbon triple bond, is 120 picometers in bond length, and its bond energy is 839 kilojoules per mole. So again, to break apart 1 mole of carbon atoms triple bonded to other carbon atoms, it would take you 839 kilojoules per mole. Notice here, though, what you're seeing. Your triple bond is shorter and stronger than your double bond. Your double bond is shorter and stronger than your single bond. So again, where lattice energy deals with looking at, so your lattice energy is a measure of breaking up those ionic bonds. Your bond dissociation energy is the energy to break apart covalent bonds. And again, I know we saw this in a previous slide, but do not forget this. Bond breaking is always endothermic, bond formation is always exothermic. We have to remember that. So multiple bonds in bond order, again, a single bond. So one single bond is one bond sharing two electrons between two atoms. It's one pair of electrons being shared. A double bond is sharing of two pairs of electrons between two atoms. It's actually two different bonds, each holding two electrons, four electrons total being shared, but they're being shared in pairs. So two electrons in one bond, two electrons in the second bond. And triple bond is overall three bonds, but there's six electrons total being shared. Again, two electrons per type of bond. So you can see here again, your type of bond, single are the weakest, triple are the strongest. Your bond order tells you how many bonds you have in there. So bond order of 1 means one bond. A bond order of 2 means two bonds. Bond order of 3 means there's three bonds. So like O2 really likes to have a bond to itself. N2 or O2, if you have oxygen like O2 gas, that is a double bond between two oxygens. If you have a N2, which is very prevalent in the air around us, nitrogen, it's a triple bond between the two nitrogens. So you have CO2, it's two carbon oxygen bonds within the same molecule. So carbon dioxide actually looks like this. It's two carbon oxygen double bonds. Carbon monoxide is a triple bond between the carbon and the oxygen. And then again, this graph from a previous chapter, just kind of looking back at what's happening here. Why are these bonds forming? So sorry, I'm trying to draw on it, but it's not working. I'm drawing wrong on it. But your bond length is your energy minimum here. So you've got the two atoms. Over here, you can separate them out further away from each other so they're not sensing each other. So if I keep traveling this direction, eventually the atoms are so far away from each other they won't share electrons. They don't sense each other anymore. They're too far removed. I start bringing them closer and closer together, and I see the energy decreasing of the system. I'm eventually going to hit that sweet spot. This is the perfect spot where the attractive forces are equal to your repulsive forces. So again, it's the attractive force between the electrons of one atom at, the nucleus or with the protons of the other atom. The repulsive forces are the electrons of the atom that's trying to combine with the other atom, but the electrons of the atom that it's trying to combine with has electrons repelling it. Your sweet spot is where you hit that energy minimization. So your bond length is how far apart these two are. So this bond length here, how far apart are these things? When you reach that minimum, that's where you're going to see your bond length because you've reached the minimization of your bond energy. If you keep bringing them closer and closer together, you will skyrocket that energy and the compound is not stable at that point.